In this video, we will
Square.
for functions and limits. Our objective is just to refresh your memory and skill over your past learning. The review is split into 3 parts. This video is part 1 of 3, the concept check. So let's start going through it. Our first question, what is a function? Well, a function is a rule that assigns one value of the input to exactly one value of the output. Domain are all the x values, typically, the input values, and typically we would use the y values, the output, to discuss the range. The graph of a function for question 1, part B, is a picture representation of the function. It is the set of all points, all the xy pairs that will satisfy the rule. How can you tell whether a given curve is the graph of a function? Well, you can pick the points on the graph and check to see with those xy pairs, your input-output pairs, check to see if it follows the rule for the function. Question 2, we have 4 ways of representing a function. And because the directions specifically illustrate with using examples, I'll actually have to write them out instead of just speaking. 4 ways of representing a function were verbally. An example of that could be something like, very simply, add 2. We could also have numerically, referring to numbers. Well, extending this one, we could have an input-output table like 1, 2, 3, following the same rule of add 2, 1 plus 2, 2 plus 2, 3 plus 2. We could also have, it's also called visually. This particular one of x plus 2, it would just be a line. And that line does not... just the picture of that I didn't really like. It didn't look like a slope of 1 to me. That looks better. And the last one we had was algebraically. Algebraically just means equations. That would be something like y equals x plus 2. The same rule of add 2 represented 4 different ways. Verbally, numerically, visually, and algebraically. Part 3, what is an even function? An even function has this criteria. If you plug in the argument of negative x, you will get back the original function f of x. How can you tell if it's even? Even functions have y-axis symmetry. I would also like to note your answers should be written in complete sentences. I'm not writing in complete sentences just to shorten the video because you can always pause complete sentence. Examples of even functions? Well, easiest is just x squared. Other easy ones, you could say x to the 4th. And if you wanted to use a polynomial, you could actually add up even functions, x to the 4th plus x squared. That would still be even. The sums and differences of even functions are even. For part B, what is an odd function? Odd functions have a similar rule, f of negative x, but instead of getting the original, you get opposite of f of x. You can tell that they are odd if they have origin symmetry, or it's also called rotational symmetry. If you rotate the graph upside down, you should get the same thing. Even easy examples of it would be something like f of x equals x, or g of x equals x cubed. And as I mentioned before, I did the sum. On this one, I could use a difference. Those would both be even, or the blue are the even, the red are the odd. In trigonometry, some of the most famous ones that you would have for even, you could have cosine of x has y-axis symmetry, and sine of x has rotational symmetry. So some very quick trig functions, sine and cosine, are odd and even respectively. Number 4, what is an increasing function? Short definition is f of x2 is greater than f of x1 when x2 is greater than x1. Visually, that's telling us as you are going to the right, x2 greater than x1, so starting on the left, going to the right, your y value is going up as well. So the functions that kind of look like that. They never drop back downward. They're always going to be greater. Number 6, give an example of a linear function. Well, you could do this with an equation. You could do this with a graph. I'm going to choose to use algebraic. A linear function could be f of x equals 2x plus 1. We just have a line. Part B, a power function has the form of something like g of x equals x third, where the variable is the base of power. That contrasts with part C, an exponential function, because exponential functions are the exact opposite, where the exponent is, the variable is the exponent instead of the base. Part D, a quadratic function must have at most an exponent of 2. It's a polynomial of degree 2, so we could have something like 2x squared plus x minus 1. That's one type of quadratic. Part E asks for a polynomial of degree 5. So I will say p of x equals 3x to the 5th. And I can't have any exponent bigger than 5, and I just need to make sure that it fits a polynomial. For part F, we're asked for a rational function, and I'll use r of x for this one. Rational functions are always a ratio of two polynomials. It would be something of the form top polynomial, bottom polynomial. And so a very quick one we could use is just taking the same p and q that I had before. We could take 3x to the 5th minus 3x to the 4th plus 2x, top polynomial over bottom polynomial, and we'd have a rational function. Number 8, draw by hand a rough sketch of each function. Okay, I'm going to wind up erasing these pieces, and you'll note it says rough sketch, so we're not looking to have something be perfect. But we'll start off part A. Sine, peak starts off at the peak, comes down, comes up, comes down, comes up, and we should try to put a scale on it. This, of course, is 0, and progressing further, each time it's changing, these are your multiples of pi over 2, so we'd have pi over 2, pi, 3 pi over 2, 2 pi. and likewise with their negative counterparts, negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. We know it reaches a peak at 1 and bottoms off at negative 1. So here's a rough sketch for sine. Backing all this part out, and we'll go to part B. Tangent of x. Tangent of x has this format, where we had vertical asymptotes everywhere that sine was crossing. Since tangent is sine over cosine, everywhere that cosine is equal to 0, we would have a vertical asymptote. Well, putting our scale on it then, oh, I switched colors and I didn't want to. We would have cosine is equal to 0 when you have, hang on a second, I'm thinking. Cosine is equal to 0 when I'm thinking of I'm creating a mental image of the unit circle right now. My brain's a bit fuzzy. But on the unit circle, cosine is the horizontal, so that's occurring when we have 0 degrees and pi radians. So we would be looking at, this is pi, this is 2 pi, negative pi, and negative 2 pi for the vertical asymptotes. Part C, where we are asked to create the sketch of y equals 2 to the x. Well, 2 to the x, that's an exponential function. Exponential functions have this form, where it's important to note that this is the point 0, 1. And if we go over just one spot, that's the point x is 1, y is 2. You'll note the horizontal asymptote limiting down on the x-axis for the left-hand side. Part D asks us to graph y equals 1 over x. Somewhat similar in that we have asymptotes, but it will look similar to this. It closes down on both the x and y axes, knowing that we have the point like 1, 1, and we also have the point 1, negative 1. Another example of an odd function, because we could rotate this one around the origin. Oh, sorry. Part E is asking for the absolute value. Absolute value has this sharp corner V shape, where on the left-hand side, this would be y equals negative x. On the right-hand side, we had y equals positive x. For part F, we have the square root of x. Well, please note that this is, since it's using the radical symbol, this is referring to only the positive square root. Positive square root comes right through here. F. Suppose that F has a domain A and G has domain B. What is the domain of F plus G? Well, if you are taking the sum of them, it will have to be defined for both. Where you would get both of them is not the union, A or B. If you need both, you actually must have the intersection, A and B. It has to fit both criteria. Similarly, if we were looking at the domain of FG, it's the same piece. It will have to be approved for both of them. So we'd have to have A and B. But if we have the domain for F over G will have to have the domain for the top has to make sense, and the bottom has to make sense. And we also need the criteria of x values that are in the domain of B, such that g of x is not equal to 0. The second part is just going through and saying, well, f has to make sense, g has to make sense, but because we're looking at f over g, we can't have f be equal to 0. Because, I'm sorry, we can't have g be equal to 0, because if it does, then we wind up with numbers that are forcing us to divide by 0, and we know that's outside the domain. Okay, how is the composite function f of g defined? F of g of x is f of g of x. What is the domain for this one? Well, it's going to be a little bit trickier because it's not like we can just do the intersection like we had done before. When you are discussing the domain, and I think a picture may help recognize this better, when we're doing a composition, this can be our function g, this can be our function f. Now, we could actually have a situation where our domain is all this stuff in red. Using the parlance of the last problem, this could be b. When we look at the range of b, we could get some kind of messed up something, depending on what the function is, but this is g of b, mapping out all of the domain to get the range. Well, the way I drew it, g of b looks like it's completely inside f. So it looks like g of b is completely contained in the domain of f. It is possible that we could actually have something going on like this, where when we map out the domain of b, it turns into a part that is outside the realm of f, where some of it might be going on outside. In this instance, we would have to describe the domain as all the values. We could say the domain of f composed with g, and I want to rewrite this because I don't like the notation I'm using there. The domain of f composed with g is all the x values that are in the domain of g such that g of x is also in the element, or is also an element of the domain of f. Basically, this is using set builder notation to map out. When you plug it into g, it must make sense. And whatever you get out from g and then plug into f still has to make sense. Number 11, suppose the graph of f is given. Write an equation for each of the graphs that are obtained from the graph of f as follows. Okay, so basically this is the transformations. We know if it's a horizontal or x-axis, or if it's an x change, that will be applied to the argument inside the parentheses. But if it's a y change, then that is going on outside the parentheses. So a shift of 2 units upward, that would be f of x plus 2 going on the outside. If we wanted to shift 2 units downward, that would be f of x minus 2, minus on the outside. Shifting to the right, though, is an x-axis change. This is a piece that has to be inside the argument, inside the parentheses, and does the opposite. So instead of going to the right, right would tend to indicate plus 2, but we're actually taking minus 2. Same thing with 2 units to the left. Inside, left is actually a plus 2 on that. Reflecting about the x-axis. X-axis tells us that we're flipping it up or down. Up or down is actually telling us outside. That's a type of Y change. And if we reflect across the Y-axis, that's a left and right. Left and right is X argument, so that would be f of negative x. G, stretching vertically. Vertical is y, so stretching means we will have to multiply on the outside. Shrinking vertically tells us it's got to get smaller, so that would be 1/2 f of x for our factor of 2. For a horizontal stretch, well, horizontal tells us inside the argument, but opposite of what we had for the y's. A stretch is actually multiplying by 1/2, and a shrink is actually multiplying by the 2. It's the opposite of what we see for the y. Number 13, describe several ways in which a limit can fail to exist. Illustrate with some sketches. Well, remember, a limit can fail to exist if we have approaching one, but not on the other. If the left-hand limit and the right-hand limit don't match up, the limit fails to exist. We can also have a limit fail to exist if it's ballooning upward toward an infinity, because the limit only exists when it closes in on some finite number. Infinity is not finite. Some other ways. We looked at if it balloons upward to positive infinity. We could also have one go downward to negative infinity, closing in on a y-asymptote, on a vertical asymptote. And you could also have limits just not exist if it's a one-sided limit. For example, if we're taking the square root of something, there is no left-hand side, so this limit can't exist there. 16. What does the squeeze theorem say? Writing up the specific details of it are basically noting if we take the limit as x is approaching some number of f of x, actually the notation we were using before is g of x, and we have the limit of f of x equal that, and we have the limit as x is approaching a of h of x equal a limit, and we are bound f of x is less than g of x for all the x values surrounding our limit. Then all of this stuff together, all of this tells us that the limit of g of x is also going to be an L. And you look at that and say, that's kind of confusing. The picture is usually a lot easier to understand. Here we have some function f of x. And here we can have some function g of x. Not g, this one's got to be h. I'm sorry. My brain was telling me something wrong for a moment. Okay. Please note at this spot in yellow, that is what we're saying for these two pieces. If we approach the same x value, the same value a, they are closing in on the same limit L. If we have a picture like this, it's the top two. If we then add in this piece in green, that in between these two for f and h, we have some function g that looks something like this, but g is in between the f and the h. If we encounter this picture, g is squeezed in between f and h, so it's forced to go to the same spot. All the stuff that we had written out in blue is the algebraic representation of the squeeze theorem, but this picture is the visual interpretation of the squeeze theorem. It is important that you should be able to work with both, because you may understand the picture of the squeeze theorem, and that's fantastic. Understanding the picture is, of course, important to it. But if you don't know how to write up the details for the algebraic interpretation in the blue, if you don't actually run through the checklist of if this works, and this works, and this happens, if you don't run through this checklist algebraically, then you may not be able to use the theorem, because what if you're not given the picture? You can still use it, you can still understand it, but knowing both makes it easier to recognize it, makes it easier to use it in other contexts besides just, oh look, I happen to see this picture is working out. 17. What does it mean for f to be continuous at a point A? Well, our definition was, if you take the limit as x is approaching a of our function, it will actually equal the function value at a. What does it mean for f to be continuous on the interval from negative infinity to infinity? That is, what does it mean for f to be continuous over all the real numbers? Well, that means it's continuous for every single point. Now, what can we say about functions like this? Well, a lot of things. If it's continuous at every single real number, we know it has to be defined for every single real number. Because if there's some, for example, if the function is not defined at x equals 3, well, if it's not defined, how could the limit equal the function value if the function value doesn't exist? Of course it can't. So one thing we would know is that the domain of f are all the real numbers, or the domain is all the real numbers. And because it's continuous, we know that with the graph, there are going to be no holes, there will be no jumps, there will be no gaps. Number 18. What does the intermediate value theorem say? This is, once again, a piece that has both the algebraic interpretation and the graphical interpretation. The intermediate value theorem says if we have f that is continuous on the closed interval a to b, and we have f of a not equal to f of b, then for every value d, and I realize these are not the letters that your textbook uses, but for every value d such that this d is on our y-axis, you'll note the way I'm writing this up assumes f of b is higher than f of a, I'm making the assumption that this is an increasing function, although strictly speaking, it's absolutely true if we had a decreasing function as well. It's easier to write it up this way and just assume with the picture that we have this piece. So what this picture is saying is, suppose we have a function that is continuous from somewhere a to b. So we have a continuous function on the interval, and we can pick, or rather note, here is f of a, there is f of b. Take any number that's in between f of a and f of b on the y-axis, like this one. Take any number d you want. The intermediate value theorem tells us there exists some number c that must be in the interval from a to b. Well, specifically, it's going to be in the open interval, such that f of c will equal that d value. Graphically, this is very, very straightforward to see. The d value that we had picked on the y-axis, if we come over to the function, we'd be able to drop straight down, and there will exist a number c that will give us the d value height that we want. This is a piece that we used extensively when we were looking at the definition, the epsilon delta definition of a limit. We used it all the time because we were saying, well, here's my epsilon, come over, get my delta. Or at least touchy-feely, missing some details, but that's what we were doing. That's our intermediate value theorem. The picture is a lot easier to understand than the actual written definition, and I did not write down the perfect 100% formal definition instead, but just kind of filled in the pieces with what the graph needed to be. So, finishing up this part of the video. This was the concept check portion of our review, just trying to refresh your memory of things that we'd already been working on and remind you of some of the skills that we've already incorporated.